The next section of our video clip is going to cover applications of proportions. Again, please always watch for the title that I put at the top of the screen to help guide you as to which section it is in your textbook. I'm not going to be numbering them by sections. I am going to be using some problems out of your book this time, however, in an effort to show some or share some examples about how to do some specific types of problems. There are three types of problems that we're going to look at when we look at these applications, or if you will, story problems. A lot of people have some trouble with this area, and so I thought it would be good to have a video on this topic. We're going to be looking at problems that involve work. And what I mean by that is Joe and Sam are going to work on a job together. Because they're going to work together on this job, they're going to do the job faster than if they did that job alone. And we'll look at that situation of how working together and how much time it will take them working together than if they had done the job alone. Again, those are called work problems. The next kind of problems in this section is going to be problems involving direct proportions. Those are very simple problems. They are things like if you work 2 hours and you make $7 an hour, then you make $14. Then if the next week you work 10 hours, then you're going to make $70 for that week. That's an example of a direct proportion. The amount you earn goes up proportionally based on your salary for the number of hours that you work. The third type of topic that we're going to study in this section is motion problems. And they're going to involve the equation distance equals rate times time. And we're going to set up tables to solve those kinds of problems. Let's go ahead and look at a work problem. The work problem that I'd like you to look at is number 2 in section 5.6. Actually, I'm just not going to give you a page number. So section 5.6 of your book, number 2. It says, Alexander can paint a room in 4 hours, and Alexandra can paint the same room in 3 hours. Working together, how long will it take them to paint the room? Here's what you have to think about in these work-related problems. If Alexander, and I'm going to write down their times, could do the whole job in 4 hours, and Alexandra could do the whole job in 3 hours. Here's something you have to think about very carefully here. If there were 2 of her, if you will, 2 of them, then cut her time in half, and they could do it together in an hour and a half. However, they're not. Alexander works a little bit slower. If there were 2 Alexanders, so 2 of the slower people, cut their time in half, and that would be 2 hours. So I expect that these 2 working together will do it somewhere between the quicker hour and a half and the slower 2 hours if they shared it with the same kind of person that they are. Here's what you have to think about, though. What we're looking for is how much time it takes them, and I'm here to do the job. And so I expect that's going to be between 1.5 and 2 hours. If I would just take the time that it takes them working together and divide it by the time that they would do it themselves. So let's just say, again, I'm making up numbers. Let's just say it was going to take 2 hours working together, and Alexander does the whole job in 4 hours. Then he would get 2/4 of the job done. Whatever time it takes them working together, divided by his time by himself, would tell you how much, or I'm going to put down here his share of the job. But again, I don't know if he's doing it for 2 hours. I just know he's doing it for T hours, and I need to add that with Alexandra's portion of the job. She's going to work for T hours too. Again, they're working together. She would do T over 3, or that portion of the job. And finally, when you add the portion that he does plus the portion that she does, they need to finish the whole job. That's it. Almost all work problems are like this, and that you've got to write an expression that represents the share of the job that, in this case, Alexander would do, plus the share of the job that Alexandra would do, and they have to finish the work. And then it just becomes a matter of solving this equation, which we learned how to do already in the previous section. That is to find the least common denominator, and that is a 12 here. And we learned that when you multiply both sides of the equation, every term, by that common denominator, that what you manage to do is you manage to get rid of the denominators. And so here, this 4 goes into here once, and 4 goes into here 3 times. 3 goes into here once, and 3 goes into here 4 times. And I have 3 times t, or 3t, 4 times t, or 4t, equals 1 times 12. I'll combine my like terms. 7t equals 12. And we'll divide both sides by 7 now. And we find out that it takes them together 12/7 of an hour, or 1 5/7 of an hour. Remember, we thought about this just to some extent. We said if there were 2 Alexanders, it would take an hour and a half. If there were 2 Alexanders, it would take 2 hours. So we expected to be between an hour and a half and 2 hours in our final answer for the time that it takes them to do the work. The next problem that I'd like to do is another work-related problem. It's number 10, again in section 5.6, in the homework section. The problem reads, Sarah takes 3 hours longer to paint a floor than Kate does. When they work together, it takes them 2 hours. How long would each take to do the job alone? Now, before we knew how long it took for them to do the job alone, now we only have a comparison with 1 hour, but we do know the total time it takes to do the job. So where before we put our question mark or the t in the numerator, now we know how much time it takes them to do the job. That's 2 hours together. Let's go ahead and look at this. Again, read the first sentence, and it says, Sarah takes 3 hours longer to paint a floor than Kate does. So I'm going to let Kate have H represent how much time it takes her to do the job alone, and then Sarah would have to be represented by H plus 3. Again, we're going to write an equation that involves the portion that Sarah does plus the portion that Kate does equals 1. That's always going to be the case. And it's always going to be the total time, in this case 2, divided by the time it would take them to do the whole job themselves. So this would be the portion of the job that Sarah would do in 2 hours. Kate would do 2H of the job in that 2 hours. And their portions have to add up to be the whole. Again, please remember in the last problem we didn't know what t was, but we knew what our denominators were. This time I know that the total time is 2, and I'm expecting that whatever h is, this is going to be 3 more than that. I need to solve this equation now, and the least common denominator for this problem is h times h plus 3. So I need to multiply every term, both sides of this equation, by h times h plus 3. And I'm going to kind of crowd this in. So over here I need to multiply this by h times h plus 3. And I need to multiply this by h times h plus 3. Having done that, my goal is to get rid of those denominators. So this h plus 3 and that h plus 3 disappears, giving me right here just a 2h. And then here, this h and this h cancel out, giving me a 2 times h plus 3. And then on the right-hand side, I have a 1h, just h, times h is h squared, times h plus 3 is 3h. And I've noticed now that I happen to have an equation that's got a squared term in it. I learned how to solve that problem back when I was using the zero product rule and when I was learning how to factor. I can only, at this point anyway, solve that problem by getting 0 on one side and all the terms on the other side. So now I've got to do some cleaning up. I'm probably going to have to clean up right here and then finish the problem on the next page. Let's go ahead and multiply here to get rid of the parentheses. And I believe that I'm going to move everything to the right-hand side because I like having my coefficient of my h squared term to be positive. So before I do that, however, I'm going to add these like terms. They add to be 4h. And again, I'm now going to try to get 0 on this side, so I'm going to subtract 4h from both sides. And I'm afraid because I'm running out of room, I'm going to go ahead and subtract the 6 on both sides as well. So I'll subtract 6. And what I have is nothing over here, and h squared minus h minus 6 on the right-hand side. Let's go ahead. I'm going to take a break here, recopy that, and finish this problem. This is the Sarah and Kate problem that they were painting the floor. I chose to recopy the problem from a few steps up because I was starting to write kind of small at the bottom of the board. I want to start there. We want to solve this equation. Again, we said that this is going to involve the zero product rule because I have an h squared term. So I was cleaning up this left-hand side. And I just wanted to remind you of doing these steps carefully. So please remember to collect your like terms first. And then go ahead. Again, my goal is to get the left-hand side to have a 0. And this is something I did 2 steps at once. And so I have 0 equals h squared minus h minus 6. The zero product rule says that to solve a problem like this, that I need to factor this side of the equation. This is a nice trinomial. Again, it's got a 1 in front of that squared term. So I need an h in the front of each of these. And I now need to put in 2 numbers whose product is a negative 6. Well, certainly one's going to have to be positive and one's negative. They have to multiply to be a negative 6, and they have to add to be a negative 1. That's the coefficient here. So I'm going to need a negative 3 and a positive 2 as my constants at the end. Again, the zero product rule said to take those factors and set them equal to 0. So I'm giving myself some space and writing each of those, set them equal to 0. I'll subtract 2 from both sides here, and I find out one of the answers for h is a negative 2. I'm going to add 3 to both sides here, and I'll find out one of the answers is 3. And what I want to remind you of is that h represented, and I'm afraid I've forgotten now, h represented the amount of time that it took Kate to do the work. Well, Kate's not going to work a negative 2 hours, so you've got to be sure to come through here and cross out that answer and say, that's not a feasible answer for this problem. This is the only feasible answer. So you're going to need to tell me that Kate will do the job alone in 3 hours, and since it took Sarah 3 hours longer than Kate, then it would take her 6 hours to do the job. And I need you to state those answers, to state that this is the correct of the possible 2, and then tell me what the other person will do in terms of time. That's the last work problem that we're going to do. Next, I'm going to look at some problems involving direct proportions. A nice example of a problem involving direct proportions is problem number 14 in Chapter 5, Section 6 again. Still, the section titled Applications of Proportions. The problem says, for the first 88 games of the 1998 season, Mark McGwire hit 37 home runs. So we're establishing a pattern or rate here. Assuming that he would continue to hit home runs at the same rate, how many would he be expected to hit in the 162-game Major League season? Here's what you need to do. Again, a direct proportion. Mark McGwire hit 88 games, he hit 37 home runs. So that's an established pattern to date. What we want to find out is what he would do, and again, I'm going to set up a ratio over here. Proportions are 2 ratios set equal to one another. What we want to know is what he would do in a 162-game season. How many home runs would he hit? If you choose to write the first fraction like this, the number of games he played over the number of home runs he hit, then in your second ratio, or your second fraction, you have to be sure to put the number of games on top and let x represent the number of home runs he's going to hit. You can write it like this, or you could have written it as, I'm going to abbreviate this a little bit, 37 home runs in 88 games is to how many home runs in 162 games. In a direct proportion, again, as long as, in this case, I put home runs over games, then I've got to put home runs over games here. And I could even, if I wanted to, put games. So I could write this one more time. I could say in 88 games, he hit 32 home runs. Then, in 162 games, how many home runs would he hit? every one of these will give you a correct answer. It doesn't matter which route you go. They all will give you the same statement. And please remember that when you solve a proportion, one of the things that we've said is that if you would set the cross products, forget about the words that are associated to this now, set the cross products equal to one another. Here we'll have 88 times x equals 37 times 162. And what we're going to do now is we're going to divide both sides by 88 in order to solve for x. And when we do that, we find out that Mark McGuire would possibly hit 68 home runs in a 162-game season if he continued on with his pattern of 37 and 88 games. Again, you know, he's almost doubled them, is kind of the situation, and the game numbers have almost doubled. Please notice that down here that had I solved this equation, I would have been taking 37 times 162, that's right here, and let it equal 88 times x, that's right here. So it would have given me the same thing. Here I would have had 88 times x, that's right here, and I would have let it equal 162 times 100 times 32. I'm sorry, looks like I've written a number incorrectly right here. I should have had a 37 right here. Somehow I just was not thinking. There you go. Either way, in terms of setting up this proportion, is going to give you the correct solution of 68 home runs. Again, a direct proportion, very simple problem. Number 16 in this very same section, 5.6, is another good example of a direct proportion. It reads 10 cubic centimeters of a normal specimen of human blood contains 1.2 grams of hemoglobin. How many grams does 32 cubic centimeters of the same blood contain? Let's go ahead and put the numbers down. 10 cubic centimeters contains 1.2 grams. I'm just going to put here of hemoglobin. I need to abbreviate. And I want to compare that to a specimen that's in size or volume of 32 cubic centimeters. I want to find out how many grams of hemoglobin would be in that sample. A larger sample than the first one, so I expect it to go up. I'll take these, please don't worry about the units. This describes this number. It's a volume. It's 10 cubic centimeters. It doesn't mean that you take the number and cube it. It is just telling you that this is a volume. So I'm going to take the 10 times the x and let it equal 1.2 times 32. And then I'm going to divide both sides by 10 to solve this problem. And I'm going to find out that x equals 3.84 grams of hemoglobin. Again, other ways to set up this problem, but I'm not going to go through those. You could use any number of. Again, got to make sure though, if I have centimeters cubed to grams, then I have centimeters cubed to grams. Or I could have flipped these. I could have put grams in the numerators. But you just have to make sure that you compare one to another appropriately, directly, if you will. The last type of problem that we're going to look at when it involves applications of proportions are motion problems, sometimes the most difficult for most students. The example I'd like you to look at with me is number 24, still again in Chapter 5, Section 6. The problem reads, the speed of the current in Catamount Creek is 3 miles per hour. Again, that's how fast the water's moving. Jackie's kayak can travel 4 miles upstream in the same time that it takes to travel 10 miles downstream. What is the speed of Jackie's kayak in still water? Here's a couple things that I need you to think of. If I'm going downstream in a boat, I'm going to have the benefit of earning, if you will, the rate of the water. The water is going to move me along or take me along with its current. So I get to add the current speed to my speed that I produce by paddling or using a motor to travel in that current. If I'm fighting that current, if I'm going upstream, I have to subtract that current. In this case, please remember that the current is traveling at 3 miles per hour. I have to take that away from the speed with which I can paddle or that I can motor up that stream. So keep that in mind as I do these kinds of problems. You need to use the distance equals rate times time formula, and you're basically going to be filling in the data. So let's go ahead again and look here. Let's do this anyway. As far as distances go, she travels 4 miles upstream when she travels 10 miles downstream. And that's again because she's fighting the current. It says that it's in the same time that it takes to travel, either of those. So I'm going to put the letter T in each of those spots for time. And then finally, what I want to find out is I want to find out how fast Jackie can paddle. Well, when she is going upstream or fighting the current, she's going to take her own, I'm going to use her own rate with which she can paddle, and she's got to subtract the current, fighting that 3 miles per hour. I'm just checking the data again. Yeah, the speed of the current is 3. When she's going downstream, she paddles at her own rate, but she gets to add the speed of the current. That's how you establish an expression for rate in this situation where I'm traveling up and downstream, and I end up going different distances in the same amount of time. Here's the equation, distance equals rate times time. That might be something that goes on your note card. And off to the right, I'm going to go ahead and say that the 4, which is the distance, equals my rate, x minus 3, times time. So I took this sentence right here and wrote an expression. In the next row, I'm going to take 10 and let it equal x plus 3 times t as well. And I want you to notice that if I would just solve both of these equations for time, because time is the same in each case, and this is the way I would do it, I'm hoping I can get away with doing it right here. If I would divide both sides right here by x minus 3, then on the left I would have 4 over x minus 3 equals time, all right? And then if I would divide both sides of this statement by x plus 3 to get t alone, again, then I would have 10 over x plus 3 equals t. Again, I'm getting rid of those and I have t alone. Well, look at what you have. You have two expressions that are equal to t. And so all we have to do is to let them equal one another, because they both represent the time that it takes to either go upstream or downstream, these different distances, because of the current. And I have the proportion that I want to work with now. This is it. This is my equation. It has one letter in it. It's got x in it. And remember, a proportion can be solved by setting the cross products equal to one another. So this 4 times this x plus 3 must equal this 10 times this x minus 3. And it's a simple linear equation to solve. I'm going to go ahead and start it, but probably not finish it. Here I'll have 4x plus 12, and here I'll have 10x minus 30. I would subtract 4x from both sides next to myself. Then I would add 30 to both sides. And then I would divide by, it looks like I end up dividing by 6. When I finish solving that, I'm going to find out that x is equal to 7 miles per hour. That's Jackie's speed. Come back here and look at it. She can paddle in her kayak at a rate of 7 miles per hour. We could even take this one step further, and we could solve for time if we wanted to with these original equations. Once we know that she paddles at 7 miles per hour, we could find time, see if it's equal. Those are some of the ways that you can check this. And then you could even check the distances after that. I'm going to try one more motion problem, and we'll conclude this section. The last motion problem that I'd like to look at is a little bit more difficult problem than the last one. Look with me at number 26, again in Chapter 5, Section 6. It reads, a barge moves at a rate of 7 kilometers per hour in still water. It travels 45 kilometers upriver and 45 kilometers downriver in a total time of 14 hours. What is the speed of the current? So we know the rate with which the barge travels this time. What we're looking to find is the rate of the current. And we also know that it travels the same distance up and down, probably because it's going to, delivering, and then returning. It travels at a rate of 7 miles per hour, but when it goes upstream, it's got to fight that current, so it's going to lose some rate, if you will. And when it goes downstream, it travels at 7 kilometers per hour, but it's going to gain the current, and so we'll add x in this case. They told us that it's a total time of 14 hours. They didn't tell us anything specific about each one of these, just that it's a total. So this is what I'm going to suggest to you. Would you notice this distance equals rate times time equation? It looks like this. If I would just take that equation and solve it for t by dividing both sides by r, I know that distance divided by rate is equal to time. So what I'm going to do is I'm going to write an expression here for time, and it's going to be represented by the distance divided by the rate. So I'm going to put in here 45 divided by 7 minus x. And this, likewise, the same thing for time for traveling downstream. And it's going to be 45 divided by 7 plus x. What's going to happen then is the time for this one plus the time for that one has to equal 45 minutes, or 14 hours. So I'll have 45 divided by 7 minus x plus 45 divided by 7 plus x, and that total has to equal 14. There's my rational equation that I have to solve. It becomes a fairly involved equation, to be honest. It's going to be one that involves an x squared term. I'm just going to say to you that the LCD is the 7 minus x times the 7 plus x. I won't be able to finish this problem. And what I'm going to do is I'm going to multiply both sides of the equation, all terms, by that 7 minus x times that 7 plus x. And as well, don't forget the 14. And so what's going to happen is this denominator and that will cancel out. The 7 plus x here and the 7 plus x here will cancel out. So on the left-hand side, I'm going to have 45 times 7 plus x, and then another 45 times 7 minus x, and that's going to equal 14 times 7 minus x times 7 plus x. I'm going to leave you to your own devices to solve the rest of this problem. It is just algebra at this point. Distribute the 45 here, distribute the 45 here, combine your like terms. I would multiply these two binomials together first and then multiply by 14. You're going to have an x squared term over here, so you're going to have to use the zero product rule in order to solve this problem. So get everything on one side, 0 on the other, then factor it. Set the factors equal to 0. And remember to only report an answer to me that's a positive answer. It turns out that the answer to this problem, the answers to this problem are x equals 2 and x equals a negative 2. You need to remember to tell me that this answer is no good and that the answer for this problem is 2, and it's 2 kilometers per hour, and that is the speed of the current. This is the end of this section. Applications of proportion. We'll go on to look at the next couple of sections on this CD.